Okay, in this video we are going to be examining membrane transport. Now, what we are talking about specifically in membrane transport is the movement of a solute from one side of a bilipid membrane to the other side. Now, this is a very simple chemistry problem because the solutes are typically hydrophilic because they are soluble in an aqueous environment. Recall that the head groups on the phospholipids that generate a bilipid membrane are charged or polar so that they can interact with the aqueous environment. But the problem is the interior of the bilipid membrane. This portion, which is encompassed by the fatty acid side chains, is hydrophobic. So we have a hydrophilic solute that must move across the membrane, and the membrane has a hydrophobic domain. So basically we have a chemistry problem. Now, if we look at the free energy change on this reaction, let's assume that we are going to be moving the solute across this membrane by simple diffusion. Simple diffusion is the movement of a solute across a membrane unaided, so there's no protein involvement. It's just simply the solute passing through this membrane. So if we look at this free energy on a reaction scale, what we would find is that we have a very large free energy barrier. This initial rise in the free energy barrier is the entrance of the solute, which is hydrophilic, into a non-compatible chemical environment, a hydrophobic environment. The increase in free energy, which is a positive change in free energy, this input of energy is required to displace water molecules and salts that are bound to the solute by non-covalent interactions, and then the solute must enter the hydrophobic domain where it is unable to form additional bonds. If it was able to form bonds with this hydrophobic domain, then we would have a release in energy. We would have a negative delta G because of the bond energy. But the delta G stays very high under these conditions. As the solute traverses the membrane, comes to the other side, then we have a negative delta G. The free energy change here is the energy given off by the solute resolubilizing in the aqueous environment because it is hydrophilic. So the solute is able to form hydrophilic bonds with the environment, being water and salts. That is a gain. So now, this thermodynamic barrier, this change here, is considered the free energy change of simple diffusion. Now the question is this possible? Yes, chemically is this possible if we have an input, an activation energy to get this reaction started. Then we can move a hydrophilic solute through a hydrophobic domain. But the problem is time. Chemically this is possible, but the time it takes to acquire this amount of free energy is very large. So the way we can do this to get around this problem is to introduce a protein in the membrane. So let me draw a couple hydrophobic domain fatty acid tails here. And this will indicate that we have now a transmembrane protein. Transmembrane means that it courses through the entire lipid bilayer. This is what we term a transporter because its job is to transport the solute from one side of a membrane to another. Now, the sole purpose of having this transporter is to reduce the amount of free energy that's needed in order to transport the solute through an incompatible environment of hydrophobic chemistry. Now, we still have to release the bound hydrogen bonds and salt bridges that are solubilizing the solute by the solvent. And so this is going to be an input of energy. However, what's important to note is that as the solute is moving through the core of this transport protein, there are interactions formed. And the solute forms bonds. And recall, when we form bonds, this is going to be a negative delta G. So the bond forming reduces. So we have an input in free energy requirement to dissociate the solvent molecules from the solute, and then we have a gain of energy as the solute reforms interactions, positive bonding, with the transporter. The next step is going to be a slight increase in delta G, and this is the energy required to release the bonds between the solute and the transporter. However, once again, as the solute comes out the other side of the membrane back into the aqueous environment, it can reform the bonds with the solvent. And that is our final drop of negative delta G. So if you recall our discussion on enzyme kinetics, that the purpose of an enzyme is to reduce the activation energy required to perform a catalytic reaction. So the catalytic activity of an enzyme is simply to reduce this amount of activation energy. In the same manner, the transporter is reducing the amount of free energy required to move a solute across a membrane. So the analogy is the same. The enzyme and transporter are performing the same function. They are reducing the amount of free energy required to drive this reaction forward. Now, for this particular transporter I've drawn, this is called facilitated diffusion. Facilitated diffusion simply means that it is protein mediated. We have a protein here that crosses the membrane that allows this reduction in activation energy to drive this solute across the membrane. Now, similar to an enzyme, that this is not going to change the equilibrium constant of this reaction, simply going to reduce the amount of free energy required to have this reaction proceed forward. This is going to be driven by the solute gradient. What this simply means is that if we have a high concentration of solute on one side of the membrane and a low concentration of solute on the opposite side of the membrane, This will dictate the direction that the solute is going to move. So under these circumstances, the solute will move to the right. However, if we have a high concentration of solute on the inside of the cell and a low concentration out, this is reversible. To calculate the free energy necessary for this reaction, we would use the same free energy calculation that we have looked at before for enzymes. As we looked at for enzymes, we saw that the direction of movement was dictated by the relationship between substrate and product concentration. So that if we have a large substrate concentration, which would be analogous to a large solute concentration on one side of the membrane, and a low product on the other side, low solute, that means we have a small number here. Take the natural log of that, and that will give us a negative delta G, indicating we are moving to the right. Now the next step is to examine why do we need these transporters to move molecules across the surface. We are primarily generating, by doing this, a solute gradient. In some cases, we want to generate what is called an electrochemical gradient. The purpose of an electrochemical gradient is to establish a gradient to perform work. Now this is where we have to examine a little bit of physics in this. If we have solutes that are a high concentration on one side of the membrane, for example sodium, and a low concentration on the other side, we have a chemical gradient. If we have a transporter here, this chemical gradient will be used to drive sodium in. Please also recall that this is going to induce a charge gradient, being the electrical gradient. If we have a higher concentration of sodium on the one side of the membrane, we have a higher concentration of positive charge. Now the physics gets into this is that when we have a gradient, we have potential energy. It is called potential energy because the gradient stores energy. Once we have a potential gradient, a potential energy gradient of either a chemical gradient and or an electrical gradient, this is stored energy now that can be used to perform work. We saw this with the entrance of glucose into intestinal cells. This principle here is best exampled by secondary active transport. In this case, we have a sodium gradient, which is much higher than the sodium concentration inside. So if this is the inside of the cell, this is the outside of the cell. Sodium concentration is higher on the outside than is in the inside. This is creating potential energy. We are going to use this potential energy by transporting glucose. This, of course, is our SGLT1 transporter, sodium glucose transporter 1. So the potential energy that is stored in this gradient of sodium, when we dissipate this potential energy, we are turning it into kinetic energy. The kinetic energy is the movement of glucose across the membrane using this cotransporter. Now, transporters come in several different varieties. We have, first of all, uniport transporters. This means a molecule is going to be moving in one direction, similar to what we've discussed here with our facilitated diffusion. We can also have symporters. In this case, we have a transporter that is moving two molecules, typically different molecules, in the same direction. Or we can have an antiporter. An antiporter is simply a transporter that will move solutes in opposite directions. Examples for these: uniport is typically facilitated diffusion. Symporters, good example of this is our SGLT1. This is typically a secondary active transporter. And an antiporter is, as we have seen, a sodium-potassium ATPase. This particular transporter uses the hydrolysis of ATP to drive sodium and potassium in opposite directions and establish a gradient. So in this case, this is primary active transport. This particular primary active transporter is now transferring the energy from ATP into establishing the gradient. So we have stored energy in ATP that's being transferred into potential energy by forming the gradient. And then the symporter, SGLT1, we are using the potential energy stored in this gradient to turn into kinetic energy to drive the entrance of glucose into the cell.